Hello, Namaste, good evening everyone. Again, welcome to PG Nuclear Physics classroom. Okay, so as you know, yesterday we discussed the Fermi theory distribution of beta particles in allowed beta decay. Allowed from at this point, the equation number 5.7 to 1, the derivation we discussed. I hope you understand the derivation and I hope you are getting whatever I am telling, and also I hope you are doing the work whatever I am assigning to you. Okay, now let us discuss the Coulomb corrections of the Fermi distribution of the emitted beta particles. We have seen that the electronic wave function, as you know, pi b is the electronic wave function, pi nu is electronic, that is neutron wave function. Pi b, the electronic wave function, is affected by the Coulomb field of the nucleus and hence cannot be a plane wave as assumed above. Actually, there are two types of Coulomb corrections. First one, this is first one, the electronic wave function is affected by the nuclear electric field. As I told you, the simplest assumption would be to treat the electron as subject to the central electrostatic field of a point nucleus and ignore the electric quadrupole and magnetic moments. The radial wave functions in this case differ from the plane wave functions in two ways. Firstly, they have different normalization near the origin, since due to the Coulomb acceleration, the time spent by them near the nucleus is different. Secondly, the relativistic electrons have different radial dependence. The Coulomb correction can be estimated in the non-relativistic limit as follows. There is Fermi distribution with the atomic number and energy. That is 2 pi nu divided by 1 minus exponential of minus 2 pi nu, where the denominator term, the leptonic wave function, is the electronic wave function in the absence of the Coulomb effect. Here neta is equals to Ze square divided by h cross nu. Please do remember. So this one, here eta is equals to Ze square divided by h cross nu. This is for electrons, and eta is equals to minus Ze square divided by h cross nu. So eta is equals to Ze square plus Ze square divided by h cross nu for electrons and minus Ze square divided by h cross nu for positrons. Z is the atomic number of the product nucleus. Nu is the velocity of the electron far away from the nucleus. The Coulomb correction increases the probability of electron emission and decreases the probability of positron emission. The Coulomb correction increases the probability of electron emission and decreases the probability of positron emission, especially at low energies. So at high energies, the Coulomb force loses its effect on the spectrum shape, which is almost the same as that calculated without Coulomb correction. I will show you the spectrum shape, how the finite mass of the element which affect on this shape of the beta ray spectrum. I will discuss you soon. For small z, eta is small, and this function f of z of e tends to 1 for both positrons and electrons. When the relativistic effect is taken into account, the nuclear Coulomb factor for a pure Coulomb field becomes, that is f of Ze, so that tends to 1 plus s exponential of pi eta divided by 2 into tau into bracket s plus I eta square divided by 1 divided by 2 tau 1 plus 2s square 2 pr raised to 2 into s minus 1. This is the expression which is found in the experiment. So they have evaluated and they have calculated and found this expression for the nuclear Coulomb factor for a pure Coulomb field. Here s is equals to, so this much, that is 1 minus alpha z square raised to 1 by 2, where alpha is equals to e square by 4 pi epsilon naught c h cross is Sommerfield's fine structure. So please do remember that is Sommerfield's fine structure constant with the numerical value, that is the alpha is nearly 1 divided by 137. So where p is the beta momentum in units of me square. For z is very less than 1 by alpha. So for this case, the distribution of beta ray energy is tends to 1. This is equivalent to 1. Okay. So in second case, another effect requiring correction is the screening of the nuclear charge by the atomic electrons, which is more important for positron emission than for electron emission. For electron emission, the maximum correction is nearly 5%. It does not depend on the beta ray energy appreciably, except at very low energies. Very low energies means less than 35 kiloelectron volt. For low energy positron emission, the correction factor may be as large as 10 for higher jet values. Okay, so this is up to what the Fermi theories of beta decay and Coulomb correction for Fermi theories of beta decay. So now let us move with the topic, that is I will open that file. Okay. Wait a while, please wait for a moment. This is 46 and I have to open the 47 page. Again I'm getting confusion. Okay. If the Coulomb correction is taken into account, the RHS equation of 5.721, that is, please see the yesterday's last equation, Fermi's theories of beta decay distribution equation, should be multiplied by the function f of z comma eb or f of z comma pb. So that is energy. This eb represents energy and pb represents the momentum. So that we get. So please note down the equations. So this one, if the number of beta particles emitted per second in the momentum range, so then the total number of emitted particle per second is n naught. Then n momentum distribution can be written like this. Please note down, where a is a constant given by a is equals to this much. The value of MIF square is uncertain in the absence of any knowledge regarding the form of the interaction operator O or the nuclear wave function Ui and UIF for initial wave function and final state. For a low transition, this term MIF square, that is matrix element term is 1, which makes, so this is equivalent to 1 for a load transition. So hence this equation reduces to A is equals to g square n naught divided by 2 pi cube c cube into h cross raised to 7. Okay. See the shape of the spectrum. See, 1 minute, I will show you a figure and you should draw the that graph, then only you understand. Please wait a moment. I will open that page. 48, so 48, okay. Here you can draw this. So see here, this figure A and figure B. Please draw these figures. This is Fermi energy distribution of the beta particles. The effects of the Coulomb force on the emitted beta positive and beta negatives are shown. The dashed curve is obtained by neglecting Coulomb effect momentum, and the B represents the figure B represents momentum distribution. Getting my point? So this one, please draw this. The figure A represents Fermi energy distribution of the beta particles. The effects of the Coulomb force on the emitted beta positive and beta negative are shown, and the dashed curve in between. So whatever saying, that is dashed curve, which represents, so which is obtained by neglecting the Coulomb effect. And this is one for momentum distribution for beta positive and beta negative. Again at z is equals to 0, that is no Coulomb effect. Okay, So we will move back to the original page. This is very important what I am saying, that is for 5 to 6 marks they will ask, that is about shape of the spectrum, how the finite mass will be affected to the shape of the spectrum of the beta particles. So see equation 5.725, this equation, please do remember this one, please note it down, this one, note it down. So equation gives the momentum distribution of the emitted beta particles. From this we can get the energy distribution as follows. The total energy of the beta particles is W is equals to total energy of the beta particles plus me into c square. So this is can be rewritten as like this. So here squaring this one, EB plus me square, that is applying A plus B whole square form, and finally we will get the expression like this, EB square plus 2 EB me square by PB square. Solving, just alternating the terms, okay, just alternating the terms here. Therefore 2 EB me square DEB is equals to this much, and finally we have to obtain the equation for PB square. So by solving those expressions we have to obtain this equation. Please, W is equals to, then you have to square it, you have to rearrange the terms, and whatever the terms are going to be cancelled, please do it and evaluate for PB square. Okay, evaluate for PB square. So that what you will get, EB into bracket EB plus 2me c square divided by c square. Hence we get from the equation 5.725. So from this equation, so we get, that is the total number of emitted per second. This is just putting the values. So this much, please write it down. C is equals to A by C cube is another constant, where EB is very small, for which is less than me into c square. Hence the equation this 5.731 gives, so which is reduced to this much, okay. For low z, f of z of PB is almost constant, that is equals to 1, which makes total number of emitted particles is equals to 0, as EB tends to 0 for both beta negative and beta positive. For higher z, we have to consider the Coulomb correction. For lower z, you have to neglect the Coulomb correction. For higher z, we have to consider the Coulomb correction. For very large eta, we get for beta negative emission. So that is tends to 2 pi eta, which is proportional to 1 divided by root of E beta. Okay, E beta. Okay, so you can refer the page number 120 using SN Ghoshal book. So again we will move to the next slide, that is okay. No, it's not opening, wait for a moment. Just please keep in touch with the previous equations, then only you understand. So again this distribution reduces to EM square into DEBE. For low energies, this is for low energies. This means that the number of zero energy beta negative particles is not 0. On the other hand, for beta positive particles of very low energy, since eta has a large negative value, we get f of z comma PB 1 divided by root of EB into exponential of minus b divided by b into root of EB, and the distribution is proportional to EM square exponential of this much into DEB. When EB tends to 0, this makes this tends to 0 because of the exponential factor. These features of the beta distribution curves are shown in figure. So this is 5.14a and 14b. It may be noted that instead of E beta, if we plot the momentum along the abscissa, then the numbers of both beta positive and negative are 0 as Pb tends to 0. As Pb tends to 0, even when the effect of the Coulomb force is taken into account. The equation 5.725, which gives k into bracket Em minus Eb, where k is a constant, and this equation shows that a plot of a function of the left hand side of the equation against Eb is a straight line with a negative slope which intersects the abscissa at Eb is equals to Em. So which intersects the abscissa at Eb is equals to Em. This type of graph known as a Curie plot. So this figure shown the Curie plot for allowed beta decay transition, which is a straight line in agreement with the, so which is well agreement with the theory. Okay. Sometimes deviations are observed in straight line Curie plots. This may be due to the following two reasons. See here, sometimes deviations are observed in straight lines. Deviations can be observed in straight line Curie plots. This may be due to the following two reasons. First one is, a forbidden transition will generally result in a concave up-type graph. The simple theory for allowed transition is to be modified in this case. Okay. And second one, I will open. And second reason is that another reason for the deviation is a complex beta spectrum due to the transitions to two or more states of the daughter nucleus. See the figure 5.16a, complex beta spectrum with two transitions. The end points are 0.63 MeV and 1.38 MeV. End points is nothing but what? The range of the beta particles. You have done the experiment in earlier semester. So this is transition W187 to redox, that is 187, producing complex beta spectrum, that is one or more elements are going to be produced during the transition process. The situation is analogous to the emission of alpha rays with a fine structure. The transitions to the upper states are usually followed by emissions of gamma rays or internal conversion of electrons, that is you can refer the 5.6b. Okay. So now let us come to the point neutrino mass, which is very important. So this one is very important. They will ask how the mass is, finite mass, neutrino mass is affected for the beta ray spectrum. They will ask. It may be noted that the theoretical shape of the beta distribution curve near the end point at Eb is equals to Em depends on the neutrino mass. A simple calculation shows that in this case the density of states is proportional to the neutrino momentum, that is to Em minus Eb raised to 1 by 2. The beta distribution curve for Me is equals to 0 then approaches the upper limit with the vertical tangent. Instead of horizontal tangent for M1 equals to 0. This is shown schematically in figure 5.17. The most recent experiments of Lubinov and other on the beta decay, there is tritium to tritium gives a value 14 electron volt, which is less than the mass of the antineutrino, that is so that 14 electron volt, this is lies, the mass of the antineutrino lies in between 14 to 46 electron volt, that is energy. See the effect of finite neutrino mass on beta distribution curve for MeV is equals to 0 when the mass of the neutrino equals to 0 and for MeV is not equals to 0. Getting my point? So this is for MV is equals to 0 and this is for MV is not equals to 0. So you can see the difference here. Okay, they have explained. A simple calculation shows that in this case the density of states is proportional to the neutrino momentum Em minus Eb raised to 1 by 2 the beta distribution curve for mu equals to 0, then approaches the upper limit with a vertical tangent instead of a horizontal tangent for mi equals to 0. This is shown schematically in this figure. Okay, I hope up to this clear. So you can read it once again, and also you can check in the Google Scholar. You just type it, how the neutrino mass is affected for the beta ray distribution graph. Then again you will get certain things regarding this neutrino mass. Okay, I hope up to this you are clear and understood, and also you are following the guidelines. Whatever I am instructing you, you are following, and I hope you are doing the best at home. Stay safe at home. Again, I will be back with you soon. Goodbye. Take care. Bye.